All right, so welcome everyone. Thank you so much to Darryl for being here. So let me introduce the speaker that we're all very excited to hear from, Professor Darryl Haggard, Professor of Physics in the McGill Space Institute. And you have a Canada Research Chair in Interstellar Astronomy?
That would be amazing. Yeah, it's in multi-messenger astronomy.
Okay, in multi-messenger astronomy. I tried to minimize it.
Interstellar makes it sound like a movie, which is like way cooler.
That's probably what came out of my head first.
Sorry for Debbie and I wonder what is multi-messenger.
Oh, so there are 4 cosmic messengers. Electromagnetic radiation, the one we're used to, the one you usually think of when you think of astronomy. Gravitational waves, which are perturbations in the fabric of space-time. Cosmic rays, which are very, very rapidly, like close to the speed of light, moving protons that we actually don't really know how they get accelerated to such high velocities. Probably in the outflows from supermassive black holes, but there are other candidates, and neutrinos. So multi-messenger is any combination, any 2 or more of those different messengers. Yeah, it's a good question.
All right, so Darryl also has an undergraduate in philosophy, which also piqued my interest simply for the fact that we're an interdisciplinary space and we bring together different perspectives. And that was the first thing I thought is, Mercy, why have we never invited you to just talk? And so I proposed a whole bunch of things that you could talk about. It could be how you merge that in your research, or even just identity in your research, or really I just left it completely open, and we're really grateful and excited to have you, so let me stop.
Thanks.
Do we want to do a really quick, because these are usually intimate discussions and it's not so big, but do you want to do a really quick roundtable so you know who you're talking to?
Yeah, that'd be great, sure.
Okay, Darius, would you begin?
I'm Darius. I work here as an assistant, and I'm a recent graduate from the neuroscience program.
My name is April. I study cognitive science and history and philosophy of science. I actually met you 2 years ago at Super Science. Nice to see you again.
Awesome, nice to see you too.
My name is Inyas. I'm in math and computer science. And 2 years ago, I spent 2 weeks at Pyramid Institute, so I'm really looking forward to your talk.
Great.
My name is Emil. I'm a law student here at McGill, and I'm just really interested in physics and whatever, but I don't understand.
I don't understand that.
I'm Nikia, and I'm studying computer science with minors in linguistics and statistics.
Thanks.
I'm Caroline. I'm studying my undergrad in piano performance and math, but I used to do engineering, so I miss doing physics.
So my name is Ryan, and I'm a third-year neuroscience student with a minor in math, and I'm still interested in physics.
Excellent, great.
I'm Jai. I've had sort of a career as a digital poet for a while, working with computers and poetry, but I love physics, so I'm very, very pleased to be here. I work here as an advisor.
Thank you.
I'm Jay, founder and co-director with Anita. I am a faculty member in literature, and I'm a frustrated scientist. Not a frustrated artist, but frustrated scientist.
Totally understand.
Catherine, would you be able to introduce yourself? Or maybe let's go to Zere.
I'm Zere. I'm study psychology, and I would be interested to know how you combine physics and philosophy.
Catherine?
Hi there, sorry about that. I'm home in St. Henri. I'm involved in the School of Continuing Studies, and specifically McGill Community for Lifelong Learning. And my background, I did do a bachelor in science and did take some astronomy. So from 40 years ago, so still interested in it.
Super. Wei?
Hi, I'm Wei, and I'm UN student, and I'm now studying economics, and I also do minor in statistics.
Super.
And Sumali said she was at the library.
Okay.
She can speak.
And Somali is biochemistry. I hope I have this right, Somali. But yeah, Somali is a very busy undergraduate in biochemistry. So glad to see you, Somali. All right, please.
Okay, so I don't have a particular agenda. We can just talk about whatever. The slides I have here, I'm happy to click through with you all, but I actually put them together about a year or so ago when I went home to my alma mater, which is, as Anita mentioned, an undergrad serving institution called St. John's College, which only does classics. So that's where the degree in philosophy comes from. We only read original texts. We started back with like Euclid's Elements and worked our way up through Einstein's theory of special relativity, reading only original works in translation. So alongside that, we read the kind of canon of ancient philosophers and more contemporary, but not very contemporary, and then also literature. And so those were sort of the three prongs. There was science, philosophy, literature, and we did 1 year, one term of like music and one term of fine arts. So we had to paint and draw and try to compose piano music, which was really sad, but fun. It was a very, very fun education, very broad. It's an entirely 100% required curriculum. So I never had any of the decisions that you all had to make about what classes to take or when. It's all prescripted. And that has, it's limiting in its way, but it's also really wonderful because there is no upperclassmen or lowerclassmen that you can't talk to about what they're reading, because everyone reads all the same things. And we did write a senior thesis, as some of you will do or have done already. And I wrote mine on Don Quixote, which I love. And I fell in love with astrophysics while I was there. We were reading Newton's Principia, and this was in our math sequence of classes. And my wonderful faculty member, who's not with us any longer, but his name was Jack Stedman, he started to describe to us how you can use the gravitational fields of solar system bodies to give what we call gravity assist to spacecraft. So you take a spacecraft and you basically sling it at a planet, and it gets a gravity boost and can get accelerated to higher velocities. It basically takes a little bit of that energy away from the planet and uses that to boost it out into the outer solar system. And I was like, you gotta be kidding, that's ridiculous. And I got really excited about that. And that was what sort of seeded this idea that maybe I would want to study astrophysics. Years later, my mom laughed at me. She was like, that's not true. I grew up in New Mexico, and even I had this sort of this New Mexican connection. The sky there is really spectacular. And my mom, the first time I submitted a proposal to the National Science Foundation, my mom mailed me my junior high school, my middle school poster, which was about what happens when galaxies collide. So she was like, you have this whole narrative about Newton's Principia that makes you sound very fancy and smart, but it actually started a lot time before that. I don't remember what I said about what happened when galaxies collide, but I don't think it was right. But in any case, so I still study what happens when galaxies collide. We think that in the heart of every galaxy is a supermassive black hole, like the one that you're looking at. And we think when you smash two galaxies together, those black holes probably collide too. Although that same concept of that gravity assist can also happen. You can, if you have a smaller black hole encounter a larger black hole, just like our spacecraft, you can actually impart a lot of momentum to that small black hole and slingshot it out of the galaxy, or stars. So we think a lot of stars actually do interact with black holes in the centers of galaxies and get tossed out to very high velocities, kind of whizzing out through the galaxy. And so these kinds of dynamics are interesting, they're relevant to a lot of the work that I do. I'm an observer. That's why this is called observing black holes, large and small, and not a theorist. I work closely with a lot of theorists. Many of you have linkages to computer science, and certainly almost all of the sciences have some programming computing component in them now, as do linguistics and other things. And so, so we all work really closely together to try to understand things. So what you're looking at here in the background is this amazing black hole image. But we can't really understand it very well. It's kind of blobby, sort of messy. It's a really, really far away thing. So we use computers to try to simulate what we think is really going on. And then we blur those simulated images, and we fake a telescope and look at the simulation through a fake telescope and try to do all the things we can do to understand what kind of information we can extract out of an image that we take that's sort of this like fuzzy donut. Many Homer Simpson jokes have come out of this image.
I get too many questions, but this one popped in my mind. Often I hear about smaller and larger black holes.
Yeah.
What makes the size? Is that the size of the original star that falls on itself?
Yeah, so super great question. So we have sort of two broad classes. I don't think I have a slide about this in my talk, but I could pull it, or the slides, I could pull it up and look. But there are two classes. We call one class stellar mass black holes, which have their origins exactly in what you said. So these are the explosions of stars. Only the most massive stars explode and become black holes. Our sun, for example, is kind of an intermediate mass star, and it will never make a black hole or a neutron star. It just doesn't have enough mass for the gravity to collapse it down beyond the repulsion of the electrons and the protons, right? So basically with a neutron star, you take the electron, you shove it into the proton, you make a neutron. That takes a lot of gravity to overcome the repulsion of those two objects. And a black hole pushes things even further, and we don't even know what happens to matter inside there. So our sun will leave behind something called a white dwarf, which is actually a remnant, kind of a hot coal in space, which is held up by the mutual repulsion of electrons. We call it electron degeneracy pressure, but it's basically just the electrons saying, no, stay away from me, I don't want to be pushed into you. That holds up the little object that will be left over by our sun. If you go up the mass scale from our sun, so everything in astronomy, because the numbers are sort of big and hard to understand, we do a lot of relative units. So we measure a lot of things in units of solar masses. So the entire sequence of stars that are hydrogen fusing are sort of anchored to our sun's mass. So if you go up the mass scale to like 40 solar masses, we're not exactly sure what the line is, sort of 20-ish, you might start getting neutron stars. 40-ish, you might start getting black holes when they end their lives. And those life endings are explosive. They are supernovae, as you sort of understood. So those leave behind black holes that have masses that have to be less than the star. So let's say you exploded a 40 solar mass star. You can't have more than 40 solar masses in the black hole, right? The maximum you could have is those 40 solar masses. And of course, the explosion throws off a lot of stuff. So call it a 20 solar mass black hole. Maybe you get half the mass back in the black hole. So these we call stellar mass black holes. They're measured really in units of tens of solar masses. At the other end, the supermassive black holes are the ones like this one that live in the centers of galaxies, and they are typically millions to billions of times the mass of our sun. They do not come from stellar explosions. We don't actually know where they come from and how they get to be so big so fast. So we can see examples of supermassive black holes, objects that have billions of times the mass of our sun, very early in the universe. We see them through the electromagnetic emission, like you're seeing here, of material falling onto the black hole. We don't see anything inside the black hole. We see the stuff that's hot outside the black hole. We call these quasars, the brightest ones that live out in the very, very distant universe. And we can observe quasars out well more than half the age of the universe ago. We use a measure called redshift to do that, which is just a Doppler shift, just like you're used to and thinking about with like a siren going by. So we see them really early, which means they had to form fast in the early universe. And how you get that much mass into that small amount of space so quickly in the early universe is actually an open question. It turns out it's really hard to shove mass into a black hole really fast because you get so much radiation, it heats up so much that actually the photon pressure, just the photons themselves start to repulse the mass back out. So you can't do it spherically. It can't all come in evenly from all sides at once. It has to come in through directed streamers. So these are really interesting. We think we see a supermassive black hole at the heart of almost every galaxy at the present day. Which means this is nature does this efficiently. We have yet to understand it.
So what are the theories for where they come from?
Yeah, so there's a lot of different ideas. So there's some ideas that maybe stars in the early universe were bigger and more massive than they are now. So they were made out of pure hydrogen, and that allowed them to be a little bit bigger. Metals, astronomers call everything that is not hydrogen. All of you who do like bio neuroceph laugh, we call everything that's not hydrogen and helium a metal. So once you start adding metals in, and these are synthesized through supernovae, these explosions or hot shocking kind of behaviors. those stars don't seem to be able to be built, the ones that are metal enriched, as massive as the ones in the early universe. But even then, even if you make a star that's say 200 times the mass of our sun, you still can't get a black hole that's millions of times the mass of our sun. So there had to be something else. Either you built pretty massive black holes early, and then you have streamers of mass falling into them. We call this accretion, and that manages to build them up very quickly. Or you merge a lot of them together at early times. Or there's also the idea that maybe under certain circumstances, you could have the direct collapse of a more massive object that has maybe 10,000 times the mass of the sun. So we don't really know exactly. There's a lot of different ideas. People are pretty excited about the direct collapse one right now because you could get something more massive to start with. It's really hard to build them big from small things. So in answer to your question, there are these two categories and we see almost nothing in the middle. Those are called intermediate mass black holes. They're very clever in their naming. And we thought we'd see a lot of these once we kind of got the techniques to figure out how to look for them, either dynamical interactions or accretion. Turns out not so much. So we don't really know where they are. Or we haven't been clever enough at figuring out the right metric for trying to search for them. We do all of this indirect, right? We are observers. I am not an experimentalist. I am an observer. I sit back and let the universe show me what it is doing, right? And so my sort of cleverness is like design of experiment more than sort of like a test. I can't break a star in my lab and see what happens. Or at least you wouldn't want me to. So yeah, it's pretty neat. Anyway, there are these two different classes. One definitely supernova related, and the other more mysterious, but clearly ubiquitous. And so we're still working. That's one of the reasons that this imaging and understanding what's going on with material very close to an event horizon of a black hole, especially a supermassive black hole, is actually really compelling. We're trying to understand what's going on. Yeah.
But do people think that maybe not that they have always been there, but when let's say the Big Bang happened, where all mass was like condensed in one point, that the mass was, I suppose, not maybe evenly distributed, and that it was maybe already a kind of mass that stuck together while like stars split out, and then they stayed there, because it seems like, as you say, maybe unlikely that they formed like by objects merging, but that it was maybe like, are there theories on this? Or?
Yeah, so I mean, you're even thinking, or at least if I understand correctly, you're thinking about things that happened even earlier. So it turns out that we actually think, have you all seen pictures of the cosmic microwave background? And it says like spotty map that people show you. So that's showing you fluctuations in temperature, but that mass density is at very early times, like really, really, really early in the kind of cosmic history of the universe. And those slight, we call them anisotropies, they're just slight deviations. So it turns out actually, if you look out and you take the temperature of the sky, it is flat. It is the most boring thing you've ever seen. It's all 2.73 degrees Kelvin, right? So the actual picture is just like blah, it's all one color. So you have to subtract off that average value, and then you have to subtract off all of the contributions from the Milky Way and subtract off nearby galaxies. And once you've subtracted off everything you can think of, what you're left with is this just like all the tiny little deviations above and below that uniform background temperature. And we think that those deviations, those slight anisotropies, are showing us where things are slightly more dense and slightly less dense at very early times in the universe. And those structures then grow throughout cosmic time. So exactly like you were saying, you have slightly more mass in one place. And as the universe grows, mass flows into those places of overdensity and out of the places that are underdense. And so indeed, I think exactly the picture you were painting is correct, that mass at very early times, it's literally quantum fluctuations, right? These tiny quantum fluctuations actually lead to tiny overdensities, and those overdensities grow to become all of the structure we see in the universe today. Everything from galaxies to black holes to stars to gas to dust, everything. And all that stuff flows into these regions that are slightly more dense. So that is indeed how you would get an overdense region, and then how you get from this sort of broad picture, right, where you've got more mass here, so gravity attracts more mass to that location, and you build up first, both not just baryonic matter like we're used to, but also dark matter. So you build up these like massive structures, and that attracts in gas that could then funnel into a black hole. So absolutely, the black holes are associated with the overdensities of material that are the imprint of that early cosmic, slight deviations above and below an average. I don't know if that was exactly your question.
Yeah, well, I mean, it's maybe something I heard from like a talk or something. I did not really understand or remember, but I think it had to do with that. Yeah, that first image of the. Yeah. So that all the structure in the universe comes out of this like very interesting, slightly non-uniform distribution of stuff, even at the quantum level, and that those little deviations are the thing that gives us. Right?
Quantum fluctuations are enough to make a change in gravity and attract matter?
So it has to do, so we imagine, and again, this is, where you start really getting toward philosophy and physics, but we imagine this expanding universe, and what that does when you imagine an expanding universe is you change the temperature structure of the universe. So basically, as you take the hot primordial soup and you expand the universe, it's going to cool. And as it cools, certain things decouple from one another. So one of the decouplings that you can imagine easily in your mind is that, in a plasma, like we had in old plasma screen televisions and stuff, the photons and the electrons they're all interacting so often that they are basically a single fluid. If you cool that plasma, the photons and the material, the electrons and the protons, start to decouple from one another, and that's when radiation streams free through material, right? So as you cool, you have a series of different types of decouplings. So quarks, combined to make up particles that we now would recognize like protons and electrons, and then the photons decouple from that, and you start to build atoms and etc. So I'm not sure if I remember your exact question now, but it is like all these little quantum fluctuations get imprinted every time two media decouple from one another. Now, once the photons have decoupled from the mass, any overdensity in that mass is imprinted on the distribution of material, and the photons are no longer disrupting it anymore, or causing it to be smoothed out, for example.
And that's enough to attract matter and time to create the stars and stuff.
Yeah, I mean, and really understanding the quantum theory of why you even had these slight, that's a whole other discipline and domain of physics. So it is, we do use cosmology to try to understand some of these theories, but in particular, as I'm sure you all have heard before, we don't have a super good way of unifying gravity into our particle theories. And so, clearly what I'm talking about is this whole gravitational thing, right? Overdensities and underdensities, that's sort of implying something about how gravity is then going to cause things to shift into those regions. But exactly how our understanding of the kind of standard model for particle physics, how you unify that to gravity is something we really just don't quite know what to do. That's really very much in the domain of theory. These are not times that we're even capable of observing very eloquently, except for through the cosmic background. Anyway, long digressions. You can tell that I was trained as a philosopher.
We love digressions.
All digressions. It's all digressions.
We never go forward.
So there's a rather wicked game at the Institute for Advanced Study near Princeton where the people in the audience try to waylay the speaker on their title slide for as long as possible. So you all are well trained for this particular game. If you ever give a talk at the IAS, just click off of your, you already won. Even if you have to go back to it after that, you win the game.
With that, are there any other questions?
There is, but do black holes because they lose radiation, do they end up disappearing?
So they don't, so they don't lose radiation. There's Hawking radiation, which might be an interesting phenomenon right at the very horizon of the black hole. And so with the very smallest black holes, ones that have 10 to the -5 times the mass of our sun, itty bitty ones, they might be able to evaporate, as people call it, due to this Hawking radiation at the edges. But that really, in the age of the universe, that really only works for very, very, very teeny, but I might even be exaggerating the mass. They're very small black holes, ones that we wouldn't have really even an observable kind of hook for understanding. Big black holes, not so much. They don't really, there's not enough mass loss due to that Hawking radiation at the edges. So they really don't give up much. They don't give up any radiation. They don't give up any mass except for very small amounts of Hawking radiation is indeed really operating, right? We can't observe it. So we talk about it, but we don't really know. My brother is a theoretical physicist, actually. He has, with a colleague of his, talked a little bit about this idea of white holes, which is where you mentioned we don't have, like, what happens to the mass, don't really know what happens to the mass in there. Mm-hmm. But you could imagine that the mass could sink down all the way down to some fundamental scaling, maybe the Planck scale, for example, and then it can't squish anymore. Like, where is it going to go? And so the idea of a white hole is that mass falls basically under gravity until you hit the Planck scale and rebounds. And that eventually all that stuff that goes down and hits that Planck surface or that Planck limit will then fly back out of the black hole and create an enormously bright event, which they call a white hole. The only problem, though this sounds really fun because he's like a bona fide quantum gravity person, is that it takes like 10 to the 30 times the age of the universe for that to happen. So for me as an observer, I'm like, whatever, that's like nothing. I'm like, go ahead, you guys have fun, but like we're never gonna see that.
Those are all my observations.
You
won't see it, but I'm right.
Yeah. So anyhow, they're still thinking about whether or not that. So his name is Hal Haggard, and he works closely with a gentleman named Carlo Rovelli, who's actually written some really nice work. Yeah. So Carlo and Hal work closely together.
That's so cool.
Yeah, and they kind of work a lot on this idea of a white hole. And whether or not there's anything observable that might be on time scale is less sort of absurd from our perspective.
I don't want to waylay this conversation, but first I should say, please, students, if anyone has a question, ask. But I kind of do have a question. Let me start out the informal. Don't get off slide one.
Yeah.
So as you were speaking, I was thinking to myself that it's almost like deterring to venture into the world of astronomy because it's so big and it's so vast and it's so unknowable and it's so unapproachable. And I'm wondering, first, what does it feel like to be in that world? And second, do you feel like you are? Like, do you have this different sensibility during the day that you're thinking about things in the context of how we're gonna, like, how the universe may evolve in billions of years and where the universe came from? Like, does that impact your being? If that question makes sense, I don't know.
Yeah, it sounds so nice, and it's giving us way too much credit. We are just as boring as everybody else. No, I think I think it is. Let me answer this in a very indirect way. So recently, my husband's also an astronomer. He studies planets around other stars, and like whether you could have life on other planets. And so our son gets really tired of us talking about work. And so he's like the only, young person in the world who ever tells his parents, I will participate in a dinner conversation if it's not about space. And so, he asked, what will we do? Because we complain about work. Work, like all people, right? Complain about school, complain about work, whatever. And so he asked us recently, if I give you $1 million, what would you do instead of astronomy? Both my husband and I were like, we can't think of anything else we do, right? So I mean, it's a really fun thing to do. It's really interesting, and when you stop and you take that perspective, it is fascinating. It's beautiful. It's really epic, right? It's really huge and awesome. But I think in a more practical way, one of the things that's very cool about astronomy is the fact that all of you are sitting here and you're interested, right? So it has a huge amount of sort of, I don't know whether cultural currency makes it sound too transactional, but something where people are excited to talk to you about your work, right? Like this is going to sound mean, apologies to my physics colleagues, but if I don't want to talk to the person sitting next to me on the airplane, and they ask me what I do, I say I'm a physicist. That's it. That's the end of the conversation. If I'm willing to talk to them for like a couple of minutes, I might say I'm an astrophysicist. And if I want to go all in for like why Pluto is no longer a planet, I'm an astronomer, right? So depending on how much I want to talk to you, I can be any one of those things. And the thing that people are super jazzed to talk to you about is astronomer. Everyone has questions about astronomy, everyone of every age across every nation I've ever been to. The previous director of the Hubble Space Telescope used to do the taxi test. So wherever he'd go in the world, he'd get in a taxi coming from the airport and he'd ask the driver, have you ever heard of the Hubble Space Telescope? And like everyone has heard of the Hubble Space Telescope across so many walks of life, right? This is a cool thing about astronomy. And another really cool thing about astronomy is that we love amateurs. And this isn't true of all sciences, right? Archaeologists are terrified of amateurs messing up their digs and their finds. You know, there are not very many fields of science where there is just a huge and robust amateur community that is in conversation with the professional community. We have amateurs worldwide who have amazing backyard telescopes, amazing kind of slightly bigger and slightly smaller than a backyard telescope. And they take observations and they integrate those observations into our professional studies. Like we are talking to one another all the time. And so that's also very unusual as a science to have that amount of just excitement from people and also buy-in. Like every retired engineer you'll ever meet has a telescope somewhere in their house, right? And some of them have really amazing observatories, not just telescopes, you know, with full-on CCDs and digitized data, and they allow us to track stars that are varying as the globe rotates, and we can do, you know, 24-hour monitoring thanks to like this incredible network of people. Citizen science is huge in astronomy. People will classify images and feed that. So the Galaxy Zoo is a classic example of that. People did all this amazing work with these beautiful galaxy catalogs and co-wrote papers. You know, regular people, just like y'all, could sit down and, you know, classify 1,000 galaxies and co-write a paper with a bunch of astronomers at the Adler Planetarium about galaxy morphology. So it's a wonderful science that way. It's big in the sort of vastness of space, but it's also very big in its tent. Like the tent is very large in astronomy, and it's a very welcoming field. That's one of the things I love about it. Physics, not so much. It's funny because we're very adjacent, but like physics is not so able to have that dialogue somehow culturally as much. I don't know whether that was really your question or not, but
that was a great answer.
Oh, go ahead.
I wanted to ask a question about, well, I did a little bit of research about you before I came here, and I saw that some places say that you got your BA in philosophy, and other places say that you got your BA in philosophy and math. So I'm wondering, like,
yeah, so St. John's is funny that way. I think it could be either way. I mean, St. John's as a university doesn't actually really care what you call it. I just got like my degree from St. John's College. They don't really have a thing because, as I said, it's not really a curriculum where you like major in something. And so from the St. John's perspective, they're kind of like whatever. From an accreditation perspective, the number of course credits that you take in philosophy and in mathematics, because you do full 4 years every single term, a math course is considered a minor or a joint major in math from like a US accreditation university perspective. So I think it just gets written different places, different ways, different places.
Okay.
I would say if you wanted, so having retrained into physics after having gotten this very esoteric education, I did not know how to use a scientific calculator when I went back to school. I was completely clueless and had to do like the entirety of the math and physics curriculum for undergrads over again before I could start my graduate studies. So I would say it would be more appropriate to call it like a history of science type math degree. It's more like the history of mathematics or the history of science, I think is the way it would be most naturally seen from an institution like McGill. So we really read the historical development of those sciences more than what a contemporary mathematician would work on. We spent a lot of time deriving things on the chalkboard. It's also seminar style, right? So we never had a professor lecture. So our classes were 12 people or less always. We had to read, come in, and then the professor would say, who's going to present theorem X, and the students would have to go up. And so we did, it was all, there's no whatever lecturing in that.
Okay. Yeah, the reason I asked was I was really interested in how we were able to make the jump. I mean, maybe it was a jump and maybe it wasn't, and like whether or not you felt gate kept from the rest of the physics. But from what you said, it seems like astronomy is like pretty welcoming.
Yeah, so I knew that in order to be taken seriously, I had to get a degree in physics first. So I found myself a physics department. I'll give a very quick version. So when you graduate with a degree in classics, it's not entirely clear what you're going to do with yourself, right? And so I went off and I lived and worked in China for a year as a teacher. And then I came back and I worked in Silicon Valley for 3 or 4 years as a very blah professional. I wore a suit to work every day, and I did, very sort of corporate Silicon Valley kind of things. And then I decided it was time to go back to my studies. And so I applied in my location where I was. I went to San Francisco State University, which is if you don't know the California system, there's the UC system, the California University system, which is PhD granting. And then there's a tier of universities that are the state schools, many of which actually don't have culminating degrees at the PhD level, but do at the master's level. And so those institutions, at least the one I attended, would really specialize in training teachers who are going to get a graduate degree in some discipline, or people like me who are retraining and redirecting their career. So it was actually a department that was very expert at handling students like myself, who were educated, interested, but not proficient at the skills that you needed to be able to do the thing. So I was accepted as a conditional master's student there. And that meant that I had to complete whatever gaps. I had to fill in any gaps that I had. Turned out for me, I was 100% gap. So I had to redo all the things. They knew about my background, right? I talked to lots of people there. Many physicists are compelled by the history of science and philosophy. And so this was not like something they thought was strange. It just required a lot of remediation of topics in math and physics. So I basically did an entire undergraduate physics degree in 2 years with no electives of any kind. All I did was math and physics for 2 years. And then once I had finished that, I did a 2-year master's in physics. And then armed with that physics degree, I applied into astronomy programs. And so I basically retrained. I don't know if that was what you were wondering, but I would not say gatekeeping. It was very much a physics department with all of the trappings of the sort of stern physicist, but it was really a department that wanted more people to come into the fold and to love physics. It was like a very, very, they were training educators and people who were going to, who were excited to retrain themselves. And so they were really fantastic. I have nothing but admiration and good things to say about that. That particular physics department was really amazing.
It looks like Zere has a question.
Hi. So I was wondering, is it possible to find like philosophical thoughts by studying astronomy? Or like in your journey of studying astronomy, do you think like astronomy can teach us like the same way as philosophy as a humanity discipline?
I would say that I am not quite the right person to comment on that, because even my philosophy degree is a little bit atypical, right? So it's a classics program, not really a contemporary philosophy program. So in modern day philosophy, somebody else who's taking philosophy classes or has this expertise can just correct me, but I think of it as a much more kind of formal pursuit, right? I think of it a little bit the way I think of mathematics, is sort of having these like theorems and a very sort of formal discipline, not very far actually from a scientific sort of framework for thinking about things. And that's present in the curriculum that I was exposed to, but only in the later years when you start getting into like Kant and some of the more like sort of formalist philosophers. But the early ones were more like natural scientists, big picture thinkers, kind of more natural philosophy. So I think that big picture thing absolutely has a lot of really fun, it's connected to these ideas about origins, the origin of the universe, and the sort of natural philosophy side of it. But the formalism of philosophy is I think, it's as distinct from what I do in astrophysics as would be neuroscience or as would be any other discipline. They're not more or less natural partners. They're similar, but they're very distinct from one another. So I would not presume to ever walk into a philosophy department and say, I know all these great things I could teach you about the universe. That would be crazy, right? They are deep thinkers in their domain. In the same way that I'm a deep thinker in my domain. Could we talk to each other about cool things? Sure. Measurement, there's a philosopher here at McGill who studies measurement. What does it mean for a kilogram to be a kilogram? And what does it mean if our metric, or the thing that we measure all kilograms with, is losing mass, which it is, right? I mean, like, what? Right, so, I think there's plenty of places where you can have fun, free-ranging conversations. But I think disciplinarily, at least in our universities, the way we've got them set up now, they're pretty, they're specialized, they're hyper-specialized.
I don't know that it would be so far off, because there's different branches of philosophy, and I think you're talking more about analytical philosophy, which I don't think is actually that common. Like,
no,
took a few
this is
courses
like
on it,
the
very niche.
stereotype I have, but you don't
Yeah.
think that's true?
I don't think
So tell me about
most
the
of
other
what I read
branches.
in philosophy classes was more of the kind of broad thing. I took one class that was more analytical, and it was honestly very hard to get through.
Yeah. I mean, I think all of our disciplines, though, I know I forgot your name over in the back over there, but one of my best friends here at McGill is a linguist, right? But she's a theoretical linguist, right? So when she talks about her work, I find it just as sort of impossible to parse like what the different terms mean. And right, we have this sort of like translation or linguistic is wrong. We have problems with language, right? We specialize our language so much it's hard to talk to each other, but maybe, but then you think about language acquisition and things, and we all experience it back to our children and through being in different cultures and communities.
What's her name?
Her name is Jessica Kuhn. Yeah.
Yeah, I stuck a bit on what you said, and I found it very interesting when you mentioned how most people, when you talk to them about astronomy or planets or black holes, like they're super fascinated. And I just wonder what you think about maybe our relationship with the stars, because and the night sky, for example, because I've seen at some point someone mentioned, and I never thought of it that way, but the fact that with light pollution, we don't see this night sky as much, it might have changed a lot how we perceive it, and maybe we ask ourselves less questions about it, because we might see some stars, but we rarely see like the full majestic like Milky Way that we can see. And we tend to think that we don't see galaxies, but like we see a part of ours, but it's just not as clear when you just have stars. So maybe I was just wondering, it's like more an open question, but maybe do you think there lacks that kind of connection of people to that topic, and they're interested, but it's just we don't have maybe the kind of connection because it's such a complicated topic as well, and maybe hard to access?
Yeah, no, it's a really good question. So I definitely think, I hope all of you will start to think about a dark night sky as a natural resource that we are spending the way we spend down all of our natural resources right now, and that's it's something we should care about protecting, and that our future generations won't actually have access to. And this includes a lot of these like networks of satellites that have gone up recently, that from a professional astronomy perspective is devastating. Like I can't point a telescope in the night sky without it being streaked with satellite now. And yeah, it's wonderful for people to get the internet and have high-speed internet everywhere on the earth, but like seriously, like we can't see the sky anymore. And so it's really a problem, right? And they didn't design those networks, Starlink, and Canada has a version of this as well. They didn't design them to be dark, reflect a ton of light, which is really damaging, right? And so, for example, we have this amazing observatory called the Large Synoptic Survey Telescope, which has recently been renamed the Vera Rubin Observatory. in honor of the amazing Vera Rubin. And that is a many millions of dollars of investment, which is actually rendered very much less capable because of these satellites. Because it's designed to stare deep, and it can't stare deep with streaks of stuff going across it all the time, right? So there's our naked eye observation and the disruption of cities and city lights and things. And then there's the space junks plus just like the kind of throwing of stuff into the night sky, which to a sensitive observatory is really bright. So I think these are really very important questions, and it does change our relationship to the sky. It creates this disconnect where we have a lot of like sort of gee whiz, wow, look at that amazing thing that some space observatory sent down, and look at this explosion, and look at this galaxy, and look at this black hole, and it's all very disconnected from anything that we can attach to as something that we've observed ourselves. Like if you want to have an amazing experience, I think the most moving, just standing around in a dark field, is to have either binoculars or a decent, just like small amateur telescope in a very dark site and to look at Jupiter. It's like somebody hung a toy in the sky. It's like unreal. You can see the rings, and it's just so impressive somehow to be able to see this thing that you've seen all these amazing high fidelity images of, and just to look through a telescope and see the rings with your own eyes is really, I think, profound. And it's the same for Jupiter's moons. Carolyn Herschel was this amazing woman who spent her whole life in service to her brother, sadly, but she had, I think, 20/40 vision, and she could see Jupiter's moons just naked eye. So, can you imagine, like, oh yeah, I just went out last night and checked out Jupiter's moons, I mean, like, you just don't think you can do that, right? But you can. I've seen Jupiter's moons in a dark site out camping, out backpacking with binoculars, just handheld binoculars. And so it's really, it's sad to lose that ability to sort of take the things that, I as a professional astronomer can offer you as this like kind of image, this slightly detached thing, and I can write a paper about it, and I can tell you all the physics of the something, but to be able to connect that to something that you can see on your own, I think is really profound. It's like being able to, interact with an insect or something. It's just much more tactile somehow. And we are losing it for sure. I mean, our big cities and all of our night sky, I mean, all of our lights, like our lights are ridiculous. Nobody shields anything in cities. All you need is a shield. It's not like that changes how safe you feel in the park, right? I mean, it's not like it matters if the light is going up and down at the same time. We only care about the light that's going down. All you'd have to do is shield the dumb things, and then you would have so much darker skies. Another really devastating thing has happened, which is good, I think, environmentally, but all these LED lights that have become more common in all of our public spaces because they're cheaper and they're more efficient and they last longer and they are less polluting. They're horrible for light pollution. They're very blue in their spectrum, and they completely wash out our ability to see the night sky. So the proliferation of the sort of LED lighting and the sort of all of that type of lighting and the lack of shielding is really a big problem.
Catherine has a question.
Catherine?
Yeah, just in response to the streetlights, City of Montreal has a huge project where they're replacing all the lights, so they're downward, just downward lighting.
Yeah.
In our area, if they've done quite a few, it's really good. Also, just as a side note, growing up in Toronto in the 60s, you could see the Northern Lights regularly in winter.
Wow.
Like, and that's Toronto, never mind Montreal, we're that much further north. So it is very sad that we are losing that. And my favorite CPAC park is Lac Mégantic, and it's a dark sky zone. And the where the meteor showers are happening in August, you cannot book a site. Like, it's packed. People want that experience. They, I think they recognize it, and I think there's a few more being designated as dark sky zones. Yeah, the parks. So we're getting there.
Yeah, no, I meant to say that not so much that it's hopeless, but much more that like our advocacy for this matters. And I think you're correct.
Oh, yes, yes, yes.
Yeah, there are a lot of really wonderful dark sky organizations and a lot of things we can do, right? I mean, this is not something that like somehow changes our quality of life. It does cost some money, but to
Right.
put these kinds of shields like you're talking about, Catherine, I think is really I don't know, it's really worthwhile, right? It gives us
Yeah.
back something.
Yeah.
Yeah, Mobec Antique is amazing. You all can go up there, and there's also a really nice observatory that is used for commissioning a lot of like professional instruments, mostly ones developed at University of Montreal here.
Yeah.
Yeah, a beautiful place.
The satellites are more tricky.
Satellites are more tricky. They're more tricky. People really like having internet access in the middle of the Sahara Desert for some reason, right? So
Well, part of the problem is all the old ones that are flying around out there after their use. Like there's no end of life system set up. They're just dead floating up there.
Yeah, so we haven't regulated this very well, right? So telecommunications is the main industry that puts satellites up, and we did not require that they decommission. So entire orbits are just ruined. You can't send anything into those orbits, and you have to avoid the orbits because of space junk and debris. So yeah, I mean, all we would have had to do was sort of think ahead a little bit and imagine, that if you're going to put something up, you have to have a way of bringing it back down. But during the early space, sort of race, people were just so excited to just put anything up there, right? They didn't really think about this possibility of it getting too crowded. But yeah, and this is now accelerating, right, as telecommunications is just bigger and bigger business all the time. So I do think that there are solutions there, again, a little like Catherine was saying about, a city like Montreal putting some energy into this. If you can put, less reflective coating on your, some kind of coating on your satellites, that can help make them less reflective. But it doesn't change the fact that we actually permanently occupy orbits.
Yeah.
And those for spacecraft are really important. So decommissioning, space law, there's a space law group here at McGill that thinks about these things. So, and this is where you get into things like there's a combination of policy and philosophy and science and a lot of other things. What do we care about and what do we want to throw some energy into to try to make this something that our children can enjoy and our children's children, right? So.
Actually, I have a follow-up question to the satellite, because I heard that some telescopes we use to detect gravitational waves. We want to shield it, but just curious, since we are mentioning about satellite, would it be possible to send telescope onto the satellite? So actually, I guess we use that research for astronomy.
Yeah, we actually piggyback a lot on telecommunications rockets. So not so much on their satellites, but definitely on their, we will send payloads up with telecommunication satellites in the same payloads and the same rockets, which is more fuel efficient. And then you have things like the International Space Station, which does have observatories on it as well. So yes, absolutely, for sure. There's synergy between these things. It's not all lose-lose or anything like that.
So we can actually use them for observation.
Yes, you can. And certainly our intelligence agencies, not that I know anything about the intelligence community, but they work closely with telecommunications also. And I don't mean to be dismissive of the telecommunications industry, right? Think about sending up the Hubble Space Telescope, right? So you've got this beautiful, very expensive telescope up there, and how are you going to get the data back? Right? You actually need to be able to telecommute it down to the Earth, right? And so these are very, these different industrial and government and scientific organizations do have lots and lots of overlap and synergy. I think it's the lack of regulation and sort of forward thinking, like so many things to do with, like I said at the beginning, natural resources and how we're going to consume them. We just haven't been very careful or thoughtful about what we need to do over the long term.
Are we still going through this slide?
Do you guys want to see any of the slides? We didn't just want to stay on the first slide. I'll go through them fast. We've actually talked about a lot of the things. These are my awesome colleagues who are in my research group. I have nothing but love for all the amazing students that work with me. And you all probably have seen these before, but this is, again, I think this is a community community of people, the Haudenosaunee and the Anishinaabe, who work with us here a lot to think about astronomy through a First Nations lens, and also have a lot to say about things like using night sky for satellites rather than for looking at the stars. And then I had some things here. We've talked about all of this stuff, in particular my New Mexico pride for me and Anita here. And this is a picture of my bookshelf. Oh, you guys, it's not advancing.
It takes a few
It
seconds.
just takes a minute.
Yeah.
No, I went too fast. Anyway,
That's-
there was a moment. There we go. This was my, like, you know,
We have
actually,
a classic student who's a scholar. He would be so inspired to me.
he can come over and borrow from my library anytime. I have all this stuff in my office. And this was the thing I was talking about, just about, this is a beautiful NASA graphic. It's actually only a tiny snapshot. It's very big. It's a huge poster. And it shows the orbits of spacecraft thrown off the surface of the Earth and how they then get these gravity assists throughout the solar system, and get, you know, they make many, many passages around different solar system bodies and get thrown out into the further, more distant parts of the solar system. Anyway, I love that graphic. And now I study photons that do that. So it's basically the same thing. So these kinds of orbits we think of as being, you know, something that you can imagine as a fixed body orbiting another fixed body. But it turns out that in the case of supermassive black holes, the gravity around them is so strong that they actually basically redirect the orbits of photons in a very similar kind of way. And so I'm not really a bona fide dynamicist, but the observations that I make now, this entire image that you're seeing actually slightly counterintuitively is mostly light coming from behind the black hole, getting gravitationally lensed toward us into our field of view. And the reason it's brighter on the bottom is because that's the material that's actually flowing in our direction versus the material that's flowing opposite our direction. And this also has a beautiful native Hawaiian name, Puehi, which is actually borrowed from the Kumalipo, which is the creation poem of the native Hawaiian people, and means, in loose translation, the generative darkness of creation. The Kumalipo is a longer poem, but so anyhow, this is, you know, these are just my like little kind of hand waving slides to help get this notion about masses a little bit more. This particular black hole is in the Virgo cluster, so this one's not quite as close to home. So it's a cluster of galaxies that's nearby, but not that nearby. And this black hole, which we nicknamed M87 or Puehi if you prefer, is about 6.5 billion times the mass of our sun. And to give you a sense of scale, XKCD Comics has given us this little graphic. Obviously, the solar system's not inside this black hole, or we would all be crushed down to a very tiny nubbin, but that's sort of the rough scale of what our solar system would look like projected onto the size of this black hole. So it's both very, very large. It's larger than the size of our solar system, and very, very tiny. When you think about the fact that our solar system contains approximately 1 solar mass, and the supermassive black hole contains 6.5 billion solar masses, right? So it's really quite a lot of mass shoved into a really tiny little space. And just to keep making that connection about things, you know, being kicked around, Voyager 1 is the spacecraft we've sent out into the universe that has gone the farthest. So humans have managed to explore with physical devices something that's only roughly the scale of this black hole. And Voyager 1 has just left recently, in the last sort of 5 or 10 years, the heliopause, which is the sort of rough gravitational influence of our sun. So Voyager would be still stuck inside the supermassive black hole if we're out there. And of course, just to remind you guys, although you know this, anything can be a black hole, right? We talk about these as if these are sort of necessarily the endpoints of explosions of stars or a lot of mass emitters of galaxies, but really the whole deal with the black holes is just a lot of mass shoved into a small amount of space. And so if you take our Earth, all our oceans and our moms and our dads and our cousins, trees, whatever, and you smash it down into something that's roughly the size of a sugar cube, our Earth would be a black hole. So it's just about a lot of mass crushed into a very tiny volume. And the way my preferred way of thinking about this is basically if you think about an escape velocity, which you all know sort of intuitively, if I throw something goes some distance and falls back down. If I'm Superwoman, maybe I can throw it pretty hard, and I can, if I get it up to something like 11 kilometers per second, I could actually get it into orbit around the Earth. And if I push it a little harder than that, accelerate it a little bit more than that, I can actually get it outside of the Earth's gravity. A black hole, that escape velocity, for our Earth, it's 11 kilometers per second. For a black hole, it's the speed of light. So photons are trapped the same way my baseball is trapped. So they can't get out, which is why we say nothing comes back out of a black hole. So no information, no light, no magnetic fields, no mass, no nothing. And you get very high escape velocities by crushing a lot of mass down into a very small space. You just increase the gravity a lot. So this is a very beautiful sort of night sky image taken from Chile. The first part of that zoom in was looking out over the ALMA observatories. So astronomy is amazing because this is all data. This is real data. This is really our night sky. This is not a computer simulation. I didn't do this to dupe you. And if we actually now have these amazing all sky surveys. We just whizzed past, probably 300 galaxies. And we zoom into the heart of this so-called Virgo cluster, and we find this galaxy M87 or Kawaki, and we come in along this very long jet all the way in toward the middle. And if you keep zooming and keep zooming and keep zooming and keep zooming, that's where you find the supermassive black hole. And everything you saw in that video is all astronomical data. It's really our universe. Like we really were looking at stars and galaxies.
What are those like concentric tails? Like there was one tail you go in, there was another tail you go in, there was another tail, and then there's a black hole.
Do you mean as we, oh, sorry. Yeah.
Like as we start to get, like right before we see the black hole, there's like this V shape inside
Yeah,
this other V
that's a
shape inside
jet.
this other V shape.
It's a jet. So it turns out that black holes, part of the reason it's hard to build them and make them really big is because they are really good at throwing stuff back out. And so the way an astronomer usually sort of visualizes this is you think about the black hole as being sort of spherical, and due to angular momentum, things are rotating, things flatten down into a disk, and material flows in along the disk, but the black hole is trying to kind of keep some sort of equilibrium, and it's throwing out an enormous jet. So you're coming in and you see it as a V shape, because if you imagine, here's my jet. If you're looking along the two edges, there's sort of just a buildup of stuff along the two edges from your perspective. It might be symmetric all the way around, but you're looking through more material here and here because you're seeing kind of some part of suite of angles along the side. And that's why you see that jet as looking sort of like a V.
How come there's two of them though? It's like a Russian doll a little bit.
That's probably just the different scales we're probing.
Okay.
It's probably a smooth structure, and it's a helical structure. So usually the way, I don't remember whether maybe I have another video that has, I don't remember whether this one has something jetty in it. But this is sort of like this is now a not data. This is now a simulated look at what this accretion looks like, and this is really intended to show you the photon orbit. So these little tiny projectiles in here, photons orbiting around the supermassive black hole inside the inner part of the accretion disk. And you'll start to see this gravitational lensing. At this point, the observer is off the side of the screen. This is happening symmetrically in all directions, but this is trying to just help you understand why you see that ring-shaped structure. The photons, you see the ones that have been gravitationally lensed into your field of view. But the jet is symmetric in two directions. And probably the reason that you see it as sort of seeming like it's a structure one size, that has sort of one, we call it an opening angle, kind of one size here, and then it looks like maybe it's a smaller size here that wouldn't necessarily, that would fit sort of inside the larger one, has to do with the fact that we look at different wavelengths, and those different wavelengths probe slightly different parts of the structure. So it might look kind of like it's one thing embedded inside of another, just because you're looking at it through a different wavelength of light. But we think it's all one continuous structure, and it has this kind of helical shape. We think it's made by magnetic fields that are twisted, and they basically accelerate particles along this kind of helix of material out to like ridiculously large distances, like really, really far out from the black hole. Again, another thing we don't really understand exactly how they work. And this is sort of a look at how you build up. This is a very cool video showing the different, so it's going to show you different photon interactions. So this is a zeroth, like glancing blow, like glancing interaction between a couple of photons. So this is these, like a whole bunch of photons have this kind of one slight redirection due to the black hole. But then it turns out that photons can have more complicated orbits. So here you'll see it when it wrapped around rather than just once being redirected. And then we can go to even, and that's going to give you a much finer, tighter ring of photons, these ones that have a slightly more complex interaction. And then as you move to higher and higher order interactions, so here you'll see they get bent twice. So instead of just a single bending, there's two bendings. And this makes an even more thin ring of photons. And basically when we look at that black hole image, what we're seeing is a superposition of all of these different types of interactions. And so you see this very diffuse structure from the less sort of close hits, and then also that photon ring from the more higher order, sorry. What happened? YouTube wants to know. Okay. Anyhow, that's a very pretty video, and something we're hoping as we get better and better quality images to actually be able to see that photon ring, that sharper structure that comes from multiple bendings of the photons as they go around the supermassive black hole. Okay, I think there's not that many slides left in here. So we do a lot of this like very, very precise imaging using this thing called the Event Horizon Telescope, which is not a monolithic telescope. It's actually lots of telescopes spread all over the world, which in and of itself is an interesting sociological thing. We just finished our campaign from this year, like 2 days ago. And it is amazingly hard to get, I don't know, we have more than this. It's either 8 or 10 telescopes all across the world to all have really good weather all at the same time and no technical problems. So one night there's too much wind in this place, another night there's, something else is wrong in that place, and another night something
There
goes
has to
wrong.
be good visibility or seeing conditions
Everywhere.
Wow.
All across the whole world for many, many hours at a time. And so part of the reason you look at these and you're like, oh yeah, that's cool, amazing. We build an Earth-sized telescope, wonderful, but it turns out that's actually really quite hard. Sometimes we've had, trouble actually even just with security at some of the observatories. And so, there's a lot of human element to all of this, and then you have to deal with just weather as well. So it's fun to do, but it's really quite a lot of work. It takes a lot of people from a lot of places all around the world. So this is a very international collaboration, a very fun group of people who also fight a lot. This is that same, maybe this is actually getting a little bit at your question. So this is the same jet, but now you're seeing it, there's that funny thing across the top, but you're seeing it at larger scales, and you can see it does seem to have this kind of this sort of V shape, but that's just because it's a cone basically, and you're looking on two sides. It's too bad you can't see the big lobes out at large distances, but we call these jets and other winds and things feedback, and it's a way that this tiny little structure in the middle of the galaxy seems to be able to impact the entire galaxy out at even very, very large scales. So this is at radio wavelengths, which is similar to where the black hole image is from, and this is at X-ray wavelengths, so looking at very hot gas. And that jet is the same jet. And then you can see out at larger radii, there's also all sorts of like interesting magnetic structures and shock heating and stuff. So we've already talked through most of this. Oh, and then just to say, oh, my pleasure, and I'll wrap up because I know everybody's tired. The other thing that we study sometimes in my research group is gravitational radiation, which we started talking about at the very beginning about different messengers. And so this is a little NASA video of 2 neutron stars in orbit around one another that smash together and collide and send out a big burst of gravitational radiation and create a big explosion, which we call a kilonova. And so this type of object was detected via gravitational waves and light for the first time in 2018. And so our group here at McGill is very excited to be a part of that. And then I have this little plot. It's called masses in the stellar graveyard up at the top. And this is where we started, not quite understanding exactly how large the population would be. This is where we are right now. So all the blue dots you see here are all black holes detected via gravitational radiation. So we detect them because they're in a binary system like that one that you saw in the little video. And they merge together. So I think you were asking about this. They merge together and build a bigger black hole. And so this is something that we really didn't have access to as a observation until just recently. 2015 was the first time a gravitational wave signature was detected astrophysically. And then the other colored dots are showing you what we can probe in this mass range. These are stellar mass black holes. using just light, using electromagnetic radiation. And so in order to see a black hole in light, you have to have some mass around the outside. We can't just see naked black holes wandering the universe. They might be there, but we can't see them unless they interact with something else, whether it's matter or another black hole or something. And so this is what we're up to a lot. So my group has worked a little bit on this. The video I showed you of the first neutron star mergers, and this is 2 neutron stars smashing together. And the remnant that they made, we're not sure if it was a black hole or a neutron star. We can't quite tell the difference in our observations. And then there's also a black hole and a neutron star merging together, which almost certainly gives you a black hole. I'll skip over this stuff. But this has been exciting to the public. Obviously, everybody loves black holes. We've got two Nobel Prizes for black holes just in recent years. The first one was for those gravitational waves, and the second one was for this really cool discovery of the supermassive black hole at the heart of the Milky Way galaxy, which was discovered because of the gravitational interaction of these stars. The little rainbow dots are actually real stars orbiting around empty space. The little white star is just there to guide your eye. So this is another way that we might know, we'll be able to figure out if the black hole is there, if it's gravitationally interacting with the bodies. And this black hole is not completely silent electromagnetically. We actually do have event horizon telescope observations of it, which if you're nice to me, I'll show you in May. So that was it. And then those are all of my slides. Now you've seen all the slides. We didn't spend the entire time on the first slide. So anyway, it's pretty fun. We have a good time. We use lots of telescopes to look at black holes. That's not quite as fun as actually talking to all of you.
I feel like there must be other questions. But I'm going to keep mine quiet, but I do have two.
I also have one, but I'll.
Can I ask, like, do you have, because these are huge accomplishments, right? Like at a sociological level and scientific level, they're just massive and everything. You're an observer, you're not a theorist, and not the third term, which I've forgotten, which is.
I mean, I'm not an experimentalist in the sense that I can't take 2 neutron stars in my lab and smash them together and watch the explosion, because that would destroy you and me and everything.
Yeah.
Yeah.
So my question was leading towards what are you observing, and like what questions concern you now, and do they ever lead you to consider these really paradoxical space, gravitational, space-time emergence, questions like this, cosmological origins, quantum foam, all that weird stuff that's going on? Does the work converge there, or where does an observationalist sit in that?
Yeah, so I would say I am not that kind of observer, but we have many people at McGill who are. So the ones who are really trying to use, so mostly in astronomy, we mostly use electromagnetic radiation. So in general, when somebody tells you they're an observer, they're almost always looking at light. Not exclusively. As of 2015, we have these new amazing detectors that can look at gravitational waves. We also have some really cool detectors that are deployed now, usually deep underground or underneath the ocean, which are able to detect neutrinos, which are very elusive little particles. You know, there are 30,000 neutrinos flowing through me right now, but I can't detect them and you can't either. But we can with very sensitive detectors. We have another faculty member here, Thomas Gruner, who works on neutrino studies. And then cosmic rays, yeah, nobody really, I mean, those are protons, we know what they are, we just don't know how they got to go so fast. So, but mostly to 0th order, if somebody tells you they're an observer, they're looking at light. We've learned a lot from light. Almost everything we've talked about today comes from looking at light signatures. And this is also true of a cosmologist, like the kind of person you're thinking of. They're typically also looking at light. They do a much deeper song and dance about the cosmic microwave background that I mentioned. So you can extract quite a bit of cosmological information out of those interesting anisotropes in the cosmic microwave background. You also can look at this era. So Adrian Liu, I don't know if have you guys ever talked to Adrian Liu in this forum?
Heard about.
No.
Okay.
If you think we should, we will.
Oh yeah, he's wonderful. So he'll tell you a lot about cosmology at the epoch of reionization. And that's when the universe evolved just under gravity for a long time. And it wasn't until gravity brought mass into dense enough configurations that fusion started in the cores of stars. And so there was a long period where you had hot gas everywhere, so maybe the universe was kind of brighter. And then there was a long time where it just became very dark. We actually call it the dark ages. Stuff was clumping together, but there's really not much source of radiation. Things are quite cold. They're not very dense. And so there's a long period of cosmic history where things are really just quite passively evolving under the influence of gravity. And then stars turn on. And the second stars turn on, well, second in cosmological, tens of thousands, millions of years, that stars actually start fusing hydrogen in their core, the whole universe changes because now you have all these pockets of hot emitting sources all over the place. And they start to reionize. They take all the neutral gas and they pull all the electrons off the protons and they ionize the universe and leave it the way it looks now, which is mostly empty vacuum with photons coming to us from discrete sources that we can then study as structures in the universe. So Adrian studies the epoch of reionization, which is the end of the Dark Ages, and tries to understand a little bit about what happens to all of the gas, all the diffuse medium, and also all the ionizing photons, where do they come from? Is it all stars? Is some of it accretion onto supermassive black holes like I was showing you? Again, none of that is quite at the level that you were thinking of, like kind of foams and interesting structures about the early, that's really the domain of Robert Brandenberger, who is also a faculty member here. People who are really looking at these kind of grand unified theories, trying to understand what happens right around that early time when the universe first starts to expand, and then that expansion is, we undergo an era of inflation where things expand even faster, and all these primordial forces decouple from one another. That's really a place that an observer cannot go. It's very hard for us to look beyond reionization when everything is neutral and quiet and there's no light. We are blind. And so we tend to not observe back into those times. And we can look at the imprint, right? The cosmic microwave background is an imprint of cosmic structure on light that is coming to us, but we have to have some way, some handle, some observable. It's possible we'll get really good with this gravitational wave stuff in future generations, and we'll be able to look at ripples in the fabric of space-time that come to us, even from those sort of cosmic dawn. Stuff is interacting, it's leaving an imprint on space-time, but imagine all the different things you see in those images, all interacting and all imprinting on space-time. It's a lot to decouple those signals and be able to pull one out of that soup and understand what it's telling you.
So is that what excites you? And now is this kind of LIGO transformation of like your observational capacities and stuff?
So the things that excite me, I'm really mostly interested personally in what happens near the event horizons of black holes. So I'm really interested in these much more sort of, I think in an astronomer's view, a much more kind of microscopic look at the universe rather than this big sort of ecological view of what's going on cosmologically. So I want to know, how do photons interact with the edge of the black hole, like I was showing you here? How does mass cross the event horizon? How do you grow these black holes? For the smaller ones, what happens when they get very close, these two really, almost infinity-like perturbations in space-time, and then those move to get merge
Black holes are so cool.
and make something else.
Infinity-like perturbations in space.
Yeah, so black holes are like an infinite disruption, and you're taking two infinite disruptions and smashing them together, and then they make one. I mean, like, what the hell? How does that work? Right? So, yeah, so I'm more interested in sort of this, like, more, like niggly sort of small scale, like interactions of mass with other mass, rather than the sort of big overarching, like, how did the universe get to be like this? That's more the domain of a cosmologist, like some of the ones I named here.
Thank you.
So
I think, and yes, that's
My question was like, for Hawking radiations, like how can anything escape the event horizon? Like,
yeah, so the way Hawking radiation works, I'll just give you the Darryl's 101 version, because I can't actually do better than that. So in vacuum, we have particles and antiparticles are constantly popping into and out of existence. And so a particle and its antiparticle, when they annihilate, they go back to vacuum. And so the deal with Hawking radiation is that you have a particle-antiparticle pair decouple next to the event horizon of a black hole. For whatever reason, one of them falls across the event horizon, the other one doesn't. So you end up with emission. One of the two parts wanders off away from the event horizon of the black hole, and the other one has fallen in. And so in this way, mass that if it hadn't uncoupled would have fallen across the event horizon, actually can kind of cause this like fraying at the edge of the black hole, and a little bit of mass can kind of escape right at the, you know, kind of final last.
Is the one-on-one version that they're created just so that one is a little bit too far away, one is a little bit too close, so one goes in and one goes out?
Yeah, and it might actually be, the argument might be more mass, like one carries slightly more mass than the other. And so one of them has an easier time escaping, has a little bit of, you know, a little more momentum because it's slightly less massive. And so this is the idea of Hawking radiation, is that these particle-antiparticle pairs, which we really do think are constantly popping in and out of existence in vacuum, decouple because one falls across the event horizon, the other one sails away. As I mentioned, this is a totally theoretical framework. We have no hope of ever observing this, right? So once again, it falls in the sort of domain of white holes. Like, that sounds fun, but like, give me something I can look at if I'm going to be able to observe and say, this is telling me something about the physical world. So no diss on Stephen Hawking, he's amazing, but like, I can't use that for anything. And part of the reason I can't use that for anything is because if I know a black hole is there, it means I had to have some way of detecting it. And that means it's probably stuck in a mess, like the one that I just showed you, of photons and gas and dust. And so particle-antiparticle pairs, like, give me a break. There's no way, right? There's like a hot soup around the whole thing. There's no way I could see that tiny little vacuum phenomena blipping into and out of existence. So this is some of the, A, we wouldn't really know quite how to go looking for it, and B, even if we could find it, the signature is so tiny compared to all of the other mess of stuff that's happening around the black hole. It'd be really hard to see it. Again, maybe gravitational waves. You asked about gravitational waves in space, and so we do have a detector coming up in the future. I think it's going to launch in 2037, probably more like 2040, called LISA, which is the Laser Interferometer Space Antenna, I think LISA stands for, and it's 3 nodes that will fly in configuration out in space and send lasers back and forth to the 3 nodes and be able to detect gravitational waves from not the merger of 2 stellar mass black holes, but 2 supermassive black holes. So this puts it in a different frequency regime. You need this very large space-based detector. So maybe if we can detect a lot of things via gravitational waves, we could try to then know where they are and look for some signature like Hawking radiation, because they're not sort of surrounded by electromagnetically emitting gas and dust. It's kind of a pipe dream. Again, I'm not even sure what that observation would look like exactly, but you could then, if you have naked black holes, maybe you'd have some hope of localizing them with gravitational radiation and then trying to design some experiments with for Hawking radiation. Not super easy to do. Black holes are really hard, right? They're like they're not very giving of themselves. You have to go and hunt them.
That's the best black hole joke.
I have another question more like you as a scientist, and maybe this is like a little misguided, but when you work on like such huge questions, like how do you stay motivated when like on the day-to-day, like, cause I don't know.
Yeah, so like everybody, I study a lot of minutia, right? So you study small things to try to get at big things, right? I don't think any of us could sit down at work and be like, maybe I'll just try to figure out black holes today, right? You'd just be totally lost.
That's the impression you get.
Yeah, no, it's not quite like that. So, you know, we all get trained at, you know, so many proficiencies just come from habit. So you will learn how to do things that you do lots and lots of times over and over again. My proficiencies are using X-ray observations from space-based observatories, in particular the Chandra X-ray Observatory. So when I sit down to think about black holes, I'm usually thinking about X-rays. out of habit, if nothing else. I'm only recently starting to work on things like the Event Horizon Telescope, which is a different wavelength regime. And astronomers, in all of our wisdom, have not only separated ourselves from one another based on the objects we study, you know, I'm a stellar astronomer, I'm a galactic astronomer, I'm a black hole astronomer, but also the wavelengths we study. I'm an X-ray astronomer, I'm an IR astronomer. This is deeply embedded in the fact that the instruments we use to measure those different wavelengths are very different from each other. And so people become very allied with their wavelength as well as their subject matter. And so I am both a black hole astronomer and an X-ray astronomer, but I also do a lot of multi-wavelength stuff, looking at other observations and observatories and trying to understand that. And we are really quite, you know, sort of stuck. The way we design, you know, telescopes, if you look at them, they all look very different one to the next. And this has got everything to do with optimizing for a particular wavelength. So we can only really kind of slice up the electromagnetic spectrum in pretty narrow bins and then figure out how we can observe them. Some of that has to do with the Earth's atmosphere, right? An X-ray astronomer can never observe from the ground. I cannot receive an X-ray on the ground. That's very good for my biological system. If X-rays were hitting me, I would be in way bigger trouble than all those neutrinos, right? Bad for my biology. So if I want to study X-rays from space, I have to have a space observatory. It has to be above the atmosphere. So I do a lot of work with NASA, right? And then we end up, you know, siloed off in our agencies, right? The National Science Foundation in the US does ground-based stuff. Here it's NSERC, kind of is a little bit more overarching, but you know, the Canadian Space Agency and NASA are space-based stuff. And so then, anyway, so there's lots and lots of ways that we end up being narrower and narrower and narrower and narrower in our expertise when we sit down to think about things. So I spend a lot of time writing telescope observing proposals. As an observer, I probably write a good 20 proposals every year. Just asking for time on all of these different telescopes. The ones in space are highly competed, so those are really hard to get through. Then, of course, as a flip side of that, I also spend a lot of time sitting on telescope allocation committees, reading everybody's proposals to decide who should and shouldn't get time. But, you know, my job is mundane, like everyone else's. There's lots of tasks. You do lots and lots of tasks. And the proposal writing for someone like me is really quite fun because that's where you sit down and you say, here's this visionary thing, please give me telescope time because I want to do this XYZ cool thing. And so that's really fun. That's like writing narrative and kind of thinking about the next scientific, you know, wedge that you can put into the problems that you're trying to conceive of or think about how to do. And of course, I work in really big teams, right? And so I'm constantly on meetings and having to talk to people. So the days that I sit down and write a proposal are probably some of the few days where I'm really thinking about my science rather than like how annoying that person is in meetings, right? Like, why can't they mute themselves? I don't understand, right? So it's not like I sit down and think about the, you know, the vastness of black holes every morning. But I mean, I still love it. I still think it's really cool. But I think, you know, we do a lot of data analysis and computer programming in astrophysics. We crunch huge data sets, like really, really good data sets. So almost everyone on my team is becoming an expert in machine learning just because our data sets just keep getting bigger and bigger and bigger, and we don't even know how to look at them properly without some kind of an algorithm to help us parse those data. I think about programmatic things, you know, which kinds of observatories would be the best for doing XYZ science. Should our next generation telescopes be focused on one wavelength or on spectroscopy, which I haven't talked about at all, versus imaging? I've mostly showed you images. We kind of resonate with those a little bit more. Yeah, so lots of, I mean, I'm kind of like, as I get a little more senior, there's more strategic thinking about how we're going to try to do things collectively. But unlike some other sciences, since I can't build a laboratory in my office, it's a very collective activity. Every observatory for professionals is going to require teams of hundreds of people. They are just very expensive and they are very, very hard. They're technically just very hard to build. But I don't know how to build instruments. I'm a total loser at that. But I do a lot of coding, a lot of data analysis, and a lot of proposal writing and storytelling and stuff. So anyway, I don't know.
I have a follow-up question. Based on the fact that the resources are so scarce, like I only have like some experience with like research in math, and I was wondering if like in astrophysics in your experience there's like pressure to like study the subjects that are like hot or like, and maybe like this relates also to how you chose like your specific questions you want to study. I don't know.
Yeah, there's always that pressure. It's a great question. I think that pressure exists for all of us. Sometimes you want to study the things that are hot because, you know, they're changing, they're developing and evolving so quickly. That's one of the reasons they're hot. There's just so much going on. So I would say exoplanets has definitely been a field like that. Like we didn't know 20 years ago, we didn't know of a single other planet around a single other star, right? And now we know of thousands of them. And that's just like huge. I remember when the first exoplanet was discovered, like that's in my lifetime. And now it's this enormous field, right? So that's just exploded in the time that I've been a scientist. I don't study that, and it's not because I don't think it's really cool. I wanted to study black holes, right? So I would say the place that I started studying black holes is in these, you know, accreting, growing supermassive black holes in the centers of galaxies. And when I started in this field, it was really boring. Like it's what people did in the 70s. This is when this was the big growth area, when radio telescopes first started to discover supermassive black holes in other galaxies. And so many people flocked to that domain that it was really quite saturated. There are tons of people working in that domain. But then, you know, everything I think in science is why you should just study whatever the hell you want, whatever you think is interesting, right? So it's had a whole resurgence now with gravitational waves and the Event Horizon Telescope being able to take images. Obviously, I'm giving you examples near and dear to my own heart, but there's been a whole like fresh life breathed into that domain because of new experiments and people's excitement about new observations. And so my field's very old and kind of lumbering, honestly, compared to something like exoplanets. But things get new life when people get excited about them again.
That's a nice quote.
Yeah, so it's fun. I mean, I think you shouldn't worry too much about what's hot and what's not. You just study what you think is interesting, and an even better metric is you just pick the coolest person you can work with at any given moment. Like as you get, and certainly as I get more senior, like I just don't even work with people I don't like. I don't care if they're doing the coolest thing ever. I just cannot be bothered. Like what a pain to work with people I don't like. So we have entire space telescopes. I should not probably tell you this, but entire NASA proposed space missions where the team was selected based on like, you know, the core group of people that wanted to work together. And they just dream up a project. And then you pitch it to NASA. And who better to pitch something to NASA than a bunch of people that really like each other, right? So, and it's not like no jerks ever trickle in, but you know, if you have to pick a project, just pick the person you like to work with, and who cares if it's the most exciting, compelling project, because if you like working together, it will be the most exciting, compelling project. And so most things, as I get more senior, I try to choose that way. I was not very wise about that as a more junior scientist. I kind of did think, oh, this is like so exciting, I should do this. And then I'm still plagued by some relationships with people where I wish I like never worked with them because they're just such a pain. So I would just be your own person in it. You know, it's like parenting or something. Like you just have to do it your way. You cannot worry too much about what is, you know, the trend of the thing.
I have one more question about the intermediate black holes.
Yeah.
So we said that we expect some theories predict that they should be common, but we don't see them. Well, like either because our technology are limited or that they actually don't exist. But just curious, so for those theories that do predict them, like do they predict that they come like they arise similar to the supermassive ones at the galaxy center at the early stage, or do they form like the massive star ones that just collapse?
Yeah, so we actually think part of the reason it's so puzzling that there are so few of them is that we think it should come from both sides. So, you know, we should be able to push toward more and more massive stars and get at least, I don't know, a few hundred solar mass black hole out of a 400 solar mass star, maybe, I don't know, waving my hands. But so I should be able to find something that's more massive, maybe from the low mass end. And then if I think about galaxies and I look and I just catalog galaxies in the sky, they go all the way from like very massive galaxies all the way down to smaller and smaller and smaller galaxies, almost all the way down to like stellar clusters. They look very smooth and continuous, almost all the way down. So we know, and this is an observational bias, but we know of a supermassive black hole in all of the most massive ones, down to where we no longer are able to make very good measurements anymore. And we suspect that if you were to continue down that mass scheme and find black holes in the smaller galaxies, they should be relatively smaller black holes.
Yeah.
And so we have this sort of I don't know what, desire for simple explanations, namely massive galaxy, massive black hole, low mass galaxy, low mass black hole. There was just less stuff to build the things out of, right? But when we go and we look, it's hard to find them, the low mass ones in the low mass galaxies. So we have a lot of, they're called dwarf galaxies, a lot of small galaxies, but we don't have these dwarf galaxies don't have a lot of gas in them, seem to really have the black holes we kind of thought we'd find there. And then we have this other analog in the Milky Way. We actually do have big stellar clusters, and they're called globular clusters. We're not quite sure whether these stellar clusters like formed as a cluster, or if in fact they're dwarf galaxies that interacted with the Milky Way and got stripped apart, and all we're seeing is the core of bound stars from the central part of that dwarf galaxy, where all the outer layers have been stripped off by interactions with the Milky Way. So we call this hierarchical structure formation. We think this is how things work. You keep tossing small things together until they build bigger and bigger things. So now you've got a globular cluster. So shouldn't it have a stellar mass, like some sort of a intermediate mass black hole in the middle? So we go and we look at those, and we can't find them in there either. And it's not that doesn't mean they're not there. It means we haven't been clever enough to find them. It means either they're not there or we haven't been clever enough to find them. But so kind of coming from both sides, we're a little puzzled by not just our inability to really be more definitive about this question of what's happening in this intermediate mass range. So very interesting. I have a postdoc in my group right now, Kristen Daig, is working hard on trying to understand this from the low mass end. Really like can you build or can you find intermediate mass black holes in stellar clusters? And then I have lots of colleagues who are interested in it kind of coming down from the high mass end. And Lisa, this space-based interferometer, which you were excited about or interested in, if we have an intermediate mass black hole orbiting around a supermassive black hole, that's going to give you a very interesting gravitational wave signature. And so maybe gravitational waves will be one. Yeah, we call those extreme mass ratios. When you have something that's a very low mass, not quite as low as a stellar mass black hole, but maybe an intermediate mass black hole. And those two actually also, that kind of configuration also makes a great blender. So, I was telling you about high velocity stars at the beginning. If you have a low mass black hole or intermediate mass black hole and a supermassive black hole, and a star flies by that orbiting system, it's going to get kicked up to really high velocities. So another way that we can try to indirectly figure out whether we have a configuration like that is if we see very high velocity stars out far away in the outer reaches of a galaxy, that's an indication that they had to get tossed out there, probably through this kind of extreme mass ratio dynamic.
But like the current state is that we don't find any intermediate.
It's not that we don't find any, it's that we don't find, so we have like gazillions of low mass ones and gazillions of high mass ones. And then, astronomers make histograms like all scientists, boringest plot ever. But so we have like a whole lot of things, and then like not many.
So it's not that we can, also it's not that they don't exist. Like we still find some, but not to the level that.
Yeah, like 10. Right. And like we're talking about a field that has like millions of things in the bins, right? Well, maybe millions is an exaggeration. We have a lot of things in the bins. And we can't find very many in the middle. Like it's not zero, but it's not very far from zero in astronomers sort of cataloging and stuff. And LIGO and Virgo are helping, if you go back to this like masses in the stellar graveyard plot that I was showing. So these black holes along the top here, hopefully those will go away. Those, you see how they're in the kind of 100, this is solar masses. This is how many masses it has here.
Yeah.
Right, so these are neutron stars down here. They're typically between 1 and 2 times the mass of our sun. And then this is another gap. We don't really quite know why there's a gap between neutron stars and black holes. That's probably physics. And then you start to see, lower mass black holes. Like these are stellar explosions. We think we know where those come from. Those are from supernovae. And then you can build bigger ones by merging together a couple of the smaller ones. And so you can start to build some of these black holes up here in the 100 and 200 solar mass range. So, maybe we want to start calling something that's above 100 an intermediate mass black hole. Of course, this is just definitions now, right? But usually people still think of these as being not quite massive enough to be considered an intermediate mass black hole. Usually it's more like 10 to the 5, something like 1,000 to 10,000 times the mass of the sun. But you could imagine, do this a whole bunch of times.
Yeah.
you could make 10,000, it'd be a lot of times.
Yeah.
Then you'd have a really, really distinct gravitational wave background, right, that I was talking about before. You have some kind of underlying wiggle in the space-time that you might be able to figure out if things were merging that efficiently.
I think Zayrey, did you have a question?
Yeah, I do. This question is just out of curiosity, maybe not so like academic. So I'm wondering, like, as an astronomer, what's your opinions to science fiction movies? To be honest, some knowledge of astronomy for me comes from those movies, but I can see like some comments on the internet from scientists that those movies are unscientific and they cannot be beneficial to the public, like the sense of education. But I do think that in general public, for those knowledge, they may not be interested in like the grand astronomy textbooks. So I was just wondering, what's your thoughts on those, like on scientific science fiction movies in terms of like its influence on the public?
Yeah, no, that's a fun question. So I love science fiction. I read lots of science fiction. The Expanse series, if you guys haven't read it, actually does not screw up the science very often. It does occasionally, but mostly not too badly, except for when they just say we're explicitly breaking physics now. But so a lot of science fiction is a mix of good and bad, I would say. This is particularly true in movies where they're trying really hard to make a visual impact on their audience. So I don't know how many of you have seen Interstellar. Interstellar has this big black hole in it called Gargantua. That black hole is more massive than any black hole that we see in nature, but not by so much that it seems obviously crazy or anything. And the images that show up in the movie are actually high quality ray tracing simulations that were done by scientists. They're very high quality, very scientifically accurate images of a black hole. Now, to get it to look the way the producer wanted it to look, they had to spin the black hole unphysically fast. So, you know, scientists can always complain, okay, you gave me a black hole, you did all the physics right, and then you made it too massive and you spun it too quickly, like why, right? But it turns out it just makes the images more visually striking. So I don't know, is that misrepresenting to the, not really, to me that's sort of like, all right, then you can, you know, use that as a foil for explaining to your GR class why there's a maximal spin for black holes and why this breaks it, right? But your average person, like my mom, doesn't care whether it's spinning at, you know, 0.8 the maximal rotation or 0.98 the maximal rotation, right? It's just not that important a distinction, right? On the other hand, using that same movie as my foil, so I would say as a black hole astronomer, they did pretty well by black holes. As an exoplanet person, my husband will tell you they completely screwed up the exoplanets. So for one thing, they put a bunch of exoplanet like planets around a black hole that is accreting material. That's where the image comes from. They would be bathed in radiation. Nobody would be walking around the surfaces of any of those planets. Everybody would be dead, long dead, right? So, and then there's one where they had frozen clouds. This is the one that really pisses my husband off. He's like, clouds are frozen. Like, what do you think they are? Our clouds are also frozen. Like, that is frozen water. That is what a cloud is. Like, why do we have an exoplanet where the clouds are frozen? Like, what does that mean? All clouds are frozen, right? So in cases like that, they wanted something that looked really like, you know, impressive. And they're these like big, rigid, fixed structures, which don't really work on rotating bodies. And so, you know, the clouds are stupid, basically, and or they're making a big deal about something that we live around all the time, like frozen water in the sky, right? So I think there can be goods and bads, right? So again, as a black hole scientist, I was fine. As a planetary scientist, my husband was very stressed by that movie because it just has a lot of really dumb planetary science in it. And that's funny because planetary science is the part we think we do better, right? We're more knowledgeable about that. So maybe it's because we don't understand black holes as well that we can like put them into a movie and wave our hands at them, and that's like as good as the state of the art scientific knowledge anyway. Where with planets, we know a lot and we could do better if we wanted to. So I personally, as long as people don't take science fiction as truth in the same way that we know that superheroes cannot actually run at the speed of light, it's fine with me to depict them in movies. And if you can compel an entire generation of people But the idea of other worlds or other investigations or other possible ways of reality spinning out, I think it's actually really lovely, right? I mean, Star Wars in my generation inspired tons of people to be excited about everything from lasers to, you know, other planets and other solar systems to binary stars in the sky, which, you know, most stars are actually in binaries, it turns out. We're kind of weird that we're not. You know, there's lots that you can do to educate out of those narratives, which maybe somebody only put there with an impartial knowledge of the science, or put because it was a fun construct, right? It was an interesting idea that let you kind of play with the physics a little bit more. I like it, I'm a fan, but it doesn't mean that it's always right. I think it's just storytelling, really. I'm sure that there's problematic things like dinosaurs walking the earth and, you know, regrowing them from eggs or whatever. I'm sure there's like a million things that are wrong, but I guess I don't really mind that people fantasize. I think it's kind of fun.
And I think Anita might keep you here forever.
I know, I should probably go. My husband and son will meet me.
Did you notice I bit my tongue? I have a
Here we go. Next question, let's go.
That was really good. I'm gonna Google one of my questions. The other one I'll wonder about. Yeah, we should let you go because you've been very generous.
I should go. I don't have the time. I should definitely go.
So much.
My pleasure.
So wonderful.
Thank you so much.
Well, we don't have to chat. It's nice to talk to all of you.